So last time, and by last time I mean 2 times ago, because we had no class Tuesday, kind of talked about DDP, right? And there were some sort of extra details with that on the recorded lecture, and kind of had a little chat about like DDP doesn't natively handle constraints, which is annoying. And there's lots of kind of hacky ways of doing it that are sort of better or worse. Input constraints are okay. You can actually sort of, like Pontryagin, you can actually put the input constraints on explicitly in the backward pass and solve little QPs. But state constraints are much harder. And classically, people like use penalty methods or augmented Lagrangian methods where they basically try to stuff some sort of constraint penalty into the cost function and then do IOQR on top of that. There's pros and cons for all these things. But I think the general sort of like understanding consensus sort of attitude in the community is that DDP can be really fast, but it is not great at handling constraints. It's hard to get really tight constraint satisfaction. All the methods for kind of handling state constraints in particular in DDP are a bit of a add-on hack and, aren't necessarily the best. Okay, so any DDP questions then before we get into what we're doing today? Okay, so today we're going to talk about kind of the other major paradigm for doing nonlinear sort of optimal control, like nonlinear trajectory optimization, which are called direct methods in contrast to indirect, which is kind of shooting style, DDP style methods. These methods basically take the optimal control problem as it is without any dynamic programming kind of ideas, just discretize time and throw it into a big nonlinear programming solver. That's kind of the big idea. As a result, they're really good at dealing with arbitrary constraints. You can put any kind of constraint you want on there, and the solver will kind of take care of it for you. So that's the big thing for today. Actually, before that, we're going to do a little brief aside on a topic that kind of fits into both camps, which are kind of minimum or free time problems, which we didn't really talk about before, which show up quite a bit in practice, especially in like aerospace problems. So these are like, so before we've always fixed the time steps and fixed sort of the time horizon of our problems, right? What if you don't know what the final time should be? This happens quite a lot. So for example, like I know I need to get to some goal state. I have all these, actuator constraints at my final time, but I don't know how long it'll take. So in that kind of context, I want to leave the time variable as like a free variable for the solver to figure out. That's the free time scenario. That shows up quite often. And then the other version of that is what if I don't care about anything except getting to the goal as fast as possible? That's the other context in which it shows up a lot. There's a lot of literature on that. That's a pretty special case. And there's, in a lot of cases, what we call bang-bang solutions in those contexts, which means you slam your actuators full gas and then slam full brake the other way. And like you get this kind of switching style controller. And that is time optimal in a lot of cases. But sort of these problems show up. So we're going to talk about how to write those down and solve them numerically within the context of kind of what we've been talking about. And then, we're going to do the direct trajectory optimization story. And then kind of on top of that, right, there's these two big categories, indirect, direct. I'm basically telling you about the most popular versions of both, but there's lots and lots of variations. So in the indirect camp, we sort of talked about Pontryagin and shooting, which is kind of a first order gradient descent type thing. Not great. And then we talked about IOQR, DDP, which is kind of the second order shooting method. And those are pretty popular and work pretty well. In the direct camp, there's kind of there's really one major sort of methods. They're the most popular ones are called direct collocation. So we're going to talk about that, but there's lots of variations, direct transcription, blah, 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 of these guys. So that's what we're going to talk about. There's some fun tricks in the collocation setup that make it a little bit extra efficient and kind of some cool tricks in there. And then basically the way these methods work is you do a bunch of discretizing of the optimal control problem, and then you pretty much just stack it up and form a big nonlinear optimization problem. You get into the form of kind of a standard nonlinear program, and then you use an off-the-shelf solver to solve it in most cases. People do write custom solvers, like we do that quite a bit to get extra speed, for particular problems, but in general, like you can just write the problem down, discretize, and throw it at a commercial solver. So we're going to talk also about what those solvers look like under the hood a little bit, and just kind of one of the most common popular solution methods or class of solvers for these called sequential quadratic programming. And we'll talk a little bit about that. It's what it sounds like. Essentially, we know about Newton's method. You can basically think about this as Newton's method when you have inequality and equality constraints. You just Taylor expand everything. So you Taylor expand the objective to second order, gets you quadratic objective. Taylor expand the equality constraints to first order. Now you have linear equality constraints. Taylor expand the inequalities also to first order. Now you have linear inequalities. That's a QP, right? So basically, you Taylor expand everything. You get a QP, you solve the QP, and that basically gives you a step, like a Newton step on your nonlinear problems. You can think of it as a generalization of Newton's method that can handle inequality constraints, essentially. So that's what we're going to talk about today. All right, any questions before we get into it? Okay, here we go. So first up, we'll talk about the kind of free time stuff. So anyone know what the objective function, like the stage cost, looks like for like a minimum time problem? Like what's the little L, the stage cost for min time? Don't have any ideas? Like what are we minimizing? Minimizing time, right? Okay, so check this out. It's kind of funny. If I write it in continuous time, I'm minimizing over, say, like x of t, u of t, and then basically t final, right? So that ends up looking like if I just want to minimize the cost and I want this thing to add up to t final, what goes inside the integral? What's my little L? No. I wanted to integrate up to t final, right? 1, exactly. Yeah, so it's kind of funny, right? So 1 dt, that's the cost function for a min time problem. Okay, and then we've got the usual stuff. So we've got our dynamics constraints. And then to make these problems well posed, we need some extra constraints. In particular, for a min time problem, generally this means you've got some goal state. So x of t final equals x goal. And so this says basically you've got to get to the goal, and you've got to, the cost function is just that. But you have this goal constraint. We also need another set of constraints to make this well posed. Anyone have any thoughts on that? Like right now, what's the optimum? Like what are the optimal controls right now as I've written this? They're basically to slam this to infinity, right? Okay, so to make this not a stupid, ill-posed, pointless problem, we also need to have input constraints on this. So something like umin, Umax. So now with those input constraints and the goal constraint, the optimum for this in a lot of situations, not always, but in a lot of situations, the optimum is to basically slam the actuators full gas one way. And then when you're like at the halfway point, it's full brake. And so you just land on the goal constraint. That's called a bang bang solution. There's a little bit of theory on when that happens, but in a lot of cases, that's intuitively the answer for a lot of these things. Yeah, this is sort of a classic setup, but yeah, you can do anything, right? So you could have other things in here that in principle would lead to different solutions, right? Okay, so this is a minimum time problem. Yeah, if you put something else in the cost function that isn't just 1, that's not a minimum time problem anymore, but we would call it a free time problem. So that happens all the time too. Like you might need to optimize some other objective, but you don't know how long it's supposed to take to get there, right? In general, you wouldn't, right? So if you have a hard goal constraint, very often, if you have complicated dynamics and whatever, you're not going to know what the final time needs to be. So it's also, even in that situation, it's helpful to have the free time formulation. Okay, so this is min time, but there's other options. All right, so so this is like the theoretical continuous time version of this. In practice, when we do this numerically, the big thing is, so naively, if I set this up and I had like the way we've been doing it, this would correspond to like growing or shrinking the number of knot points, the number of time steps. So it's actually changing the dimension of our optimization problem. That's bad. We don't want to do that. So anyone have any other ideas? What else can I do? Yeah. So instead of changing the number of knot points, I'm going to change the h. I'm going to change the length of each time step. So that's the gist of the whole thing. So we're going to make h, which is our time step variable, from like our RK, in our integrator. Effectively, what they look like once you do this trick, they look like control inputs. So it looks like you're basically making the time step an additional control. So you kind of like stack it in your U and treat it like another control. And you can do that with ILQR DDP. You can also do it with the direct stuff we're talking about today. So it would look something like, right, we have like xk plus 1 equals, so let's say it's RK4. I'm going to just write f sub RK4. That would be like our go-to standard. And we're going to write it as if it's like xk, and then we'll call it u tilde k, where this u tilde is our original u, and then the time step, so hk, sort of stacked in there. So you do that, and then inside that f rk4, like you put the h in the usual way with the Runge-Kutta step, and that basically is it. Like you're done. You may also want to, though, to make this kind of like fully legit, when you think about the cost function, you might want to scale the cost function. We haven't really talked about this, but to make this all kind of line up and be correct, you also probably want to scale the cost by h. So the stage cost should also be multiplied by an h, right? Anyone think of something that can go wrong with this as I've just written it? Yeah, they can do weird things. They could also go negative, right? There's nothing in here as is, so I could make negative time. So if you naively just do this, bad things can happen. So the answer to this is sort of obvious. Like you also need, in general, almost always, if you're going to do this, you have to put additional constraints to bound h. So usually you want to lower bound it for sure at 0, but usually you want to lower bound it a little bit away from 0. And then you want to upper bound it to something reasonable so that you're not getting huge amounts of discretization error by taking giant time steps with your integrator. Okay, so the cost thing looks like, for example, your like stage costs would sort of end up doing this kind of thing, right? Okay, so that, and then one thing to note about this is, yeah, we also, like we just said, we would need constraints on the h's. Otherwise, the solver can do very weird things. And essentially like cheat physics. And like by either making the discretization error, like it can basically exploit discretization error by making h huge or negative. So we don't want that. And then the other thing to note about this, let's say this is like linear, like an LQR problem. So it's AX plus BU, linear dynamics, benign convex cost. Is this a convex problem? So linear minimum time problem like this, right? Say AX plus BU, everything's linear, bounds on U, whatever. That's all nice. What do we think? Is this a convex problem? I'm seeing some head nods. Yeah, it is not. Why not? So the h here is multiplying the dynamics, right? So it's h times ax plus h times bu. So you end up with h times x, h times u. Remember, h is like effectively a control input. So this is giving us like binary or bilinear or quadratic, basically, terms in the dynamics constraints. So the dynamics are no longer linear. So this is no longer a convex problem, even if the dynamics were originally linear, because of making the time step this additional variable. Turns out there are clever convex relaxation tricks you can play to make this convex in certain circumstances, but as is, like the generic min time, free time setup even if your dynamics are linear, it's always a non-convex problem, which is annoying. But that's in the dynamics constraints. So you remember our convexity conversation. If you have equality constraints, like the only convex equalities are linear equalities, right? So it's a subspace. As soon as you have curvature, so quadratic means it's curved, right? As soon as it's curved, the whole like 2 points connect with a line thing doesn't work anymore because the line's going to leave the curved surface. So this thing ends up being a quadratic equality constraint because it's h times u, h times x in there, breaks the whole thing. Now that's a curved manifold. Everyone cool on that? Makes sense. So this ends up being non-convex, which is unfortunate. There are, like I said, there are fancier tricks you can play to like relax this and still get a convex problem, which maybe we'll talk about if anyone wants to talk about it. Happy to. But as is, usually non-convex, even if the dynamics are linear, the like nominal, dynamics. Okay.
We don't want to change the number of mod points just because it'll take time to set.
Well, it's you're basically changing the problem then, right? It's a weird thing to think about even, right? Like what you're talking about there is like, the objective function is literally like if you have the big N, like number of time steps, it's big N is what you'd be optimizing over, which is a discrete variable. So then you have a mixed integer problem. That's like all bad. Like you can't really think about that in a sane way as like a differentiable kind of like smooth optimization problem. It's a bad thing to do.
Solve it, we should be able to, right?
It's not a standard form sort of smooth nonlinear problem. It's a discrete, like mixed discrete continuous thing because you're literally talking about optimizing over the discrete number of time steps. That's an integer variable. So now you have like a mixed integer optimization problem, which is super bad. Those are like some of the most terrible kinds of optimization problems. Like you don't want to touch that basically if you can avoid it. Okay, cool. Yeah, I mean, for a linear problem, it might be mixed integer convex, but even those can be like those are NP hard problems, and you can't really bound the runtime on them. It's bad. Like you don't want this.
Is our control still like zero or holding?
Yeah.
So like, if we're varying the concepts a lot abstractly, doesn't have their size, then like we could like able to do more control.
I mean, maybe you can switch up the discretization and do different things, but here it doesn't matter basically. You could use any interpolant you want and sort of stick with this. You don't have to use the same H at each time step. They can vary. I mean, it looks just like a control is the way to think about it. And it is zero order holded, right? Over a time step. Yeah, I don't know. Maybe I'm not following what you're asking. Okay. Okay, so that's the free time, min time story. I suppose you could think about it that way. Sure. So yeah, the F sub RK4 thing, that sort of will be, although technically not the way we've written it, right? If you write H as a control input, then it's not a time varying dynamics, right? It has that form. It does not depend on like EK or subscript K. So maybe technically not. But yeah, reasonable question, I guess. Okay, so if everyone's cool with this, we're gonna sort of get into the direct trajectory optimization story now. So this is kind of the other major paradigm that's widely used. And I think historically, like a lot of groups would be in one camp or the other. Like a lot of labs would be sort of direct or indirect labs, so to speak. So the basic strategy is really straightforward. You're gonna like take your sort of continuous optimization problem like we have up here with integrals and ODEs. You're just going to discretize everything. This is sometimes called transcription. So transcribe the continuous problem straight into like a standard form nonlinear program. And much to my frustration, nonlinear program is NLP. And in the modern era, the computer scientists like to use that for natural language processing. In here, it means nonlinear program. So yeah, just like we had, standard forms for LP, QP, SOCP that we kind of talked about for convex problems, there's sort of a standard form for nonlinear problems too. Basically, it's really generic. We're just assuming that things are differentiable so that we can do Newton's method essentially. So this looks, a standard form NLP will look kind of like this. So we're minimizing some objective function f of x, cost function subject to nonlinear inequalities, C of x, or equalities, so like C of x equals 0, and then nonlinear inequalities like D of x less than or equal to 0. And that can go either way, whatever sign you like. So this would be your cost function. These are equality constraints. So for us, this is generally going to mean dynamics constraints or gold constraints. And then, yeah, the inequality is basically any other constraints like actuator limits, et cetera, would go in here, right? And then this whole thing, right, we're going to call sort of a standard NLP. And this is kind of the setup that the standard solvers like. So in particular, like IPOpt, which is the one we're going to use in here, which is developed at CMU, actually, in the chemical engineering department, kind of takes in problems of this form. There's, SNOPT, Nitro, there's a bunch of sort of large scale NLP solvers out there. And we're usually going to assume, although sometimes this doesn't hold up, in particular, as we've kind of hinted at previously, this doesn't hold up when you have contact interactions in robotics, but usually we're going to assume that all these functions, so f, c, and d here, are C2 smooth, at least C2s. That means they have continuous first and second derivatives. It means I can take two derivatives, so I can compute a Hessian and do Newton's method, right? And there's, like I kind of said, there's lots of off-the-shelf solvers for this. For kind of large scale NLP problems. The most popular one, I would say, is probably IPOpt. Because it's open source, it's free. There's a couple of popular commercial ones in the sort of control community for doing trajectory optimization. SNOPT, which some people call SNOPT, is the other one that's really popular. That's an SQP solver. That one's been around for a long time. It is commercial. There's like free academic licenses you can get, but it's annoying. But it costs money to use it commercially. So usually people will default to IPOPT because it's free. And then another big commercial one is called Nitro, but with a K. KNITRO. I don't know, for whatever it's worth. So yeah, some examples, right, that you'll see. We're going to use IPOpt in here, which is free. And then SNOPT, which is commercial. And then Nitro, which is also a commercial one. And then, yeah, so IPOpt is an interior point method. It's a nonlinear, non-convex interior point method. So we kind of talked about this, and you know what interior point methods look like, right? It uses log barriers. So it's interior point optimizer. Go figure. SNOPT is an SQP method. So we kind of talked about SQP. We'll talk a little more about it. And yeah, it stands for sparse nonlinear optimizer. Nitro actually does both. It can switch back and forth between like an SQP kind of method or active set method and an interior point method, depending on the problem. So yeah, and that's kind of what you do. Let's see, anything else to say about this? I think that's it. Any questions about this? Yeah, so direct means we're gonna do it. So, but yeah, basically it means you massage the original optimal control problem to look like this, and then you throw it at an NLP solver, as opposed to like doing some kind of dynamics rollout backward pass, Riccati or Pontryagin type thing. So it's not using Pontryagin or dynamic programming. It's literally just take this sort of continuous time problem, discretize everything, and then make it look like that and throw it at a solver. If that makes sense. Indirect usually is synonymous with shooting. So you're doing like a dynamics rollout where you're like simulating a forward pass, and then you're doing some sort of backward pass like Riccati or, you know, co-state ODEs in the Pontryagin stuff to compute gradients and things like that. Does that make sense? So yeah, like I said, the indirect methods, what they're doing is like leveraging Pontryagin minimum principle kind of ideas and are explicitly like leveraging the control structure and usually are solving ODEs in the process. Technically, the sort of definition here is that like indirect methods, basically, the real difference is discretize then optimize or optimize then discretize. So to make that explicit, an indirect method optimizes first and gets continuous time optimality conditions, i.e. Pontryagin, and then you discretize those. So you like use an ODE solver and you do the forward backward stuff, the shooting stuff. On the other hand, the direct thing is discretize then optimize. So you first take the original continuous time problem, you discretize everything, you get a discrete time version of the problem, and then you optimize that discrete time version of the problem by shoving it in an LP solver. Does that make sense? Yeah, so it's like which order you do the discretizing and optimizing in is really kind of, I think, what it comes down to. Not really. It really depends. Like, there's a bunch of trade-offs. We'll get into like more explicitly the trade-offs after we do this, and hopefully it'll become a little bit clearer. So, okay, so this is kind of what it is. This is an NLP. So, like, very common strategy for solving NLPs that we're gonna give a quick sort of overview of, and that you can do because you have all the pieces, is sequential quadratic programming. This is what SNOPT does in particular, and many other solvers. Also, SQP is probably the most common technique for nonlinear MPC. So like almost every nonlinear MPC implementation you see on a robot is doing SQP for various reasons. Some of them do DDP, ILQR stuff, but all of the direct versions pretty much do SQP. Okay, so here's how that works. It's pretty straightforward, and it pretty much is what it sounds like. We're gonna take the nonlinear problem. We're gonna take a second order Taylor expansion of the cost, or technically of the Lagrangian, depending on if you do full Newton or Gauss Newton. And linearize the constraints. So the C of X and D of X to approximate the nonlinear problem locally as a QP. And this is basically, you know, so here's what it looks like in math, right? So I'm going to now minimize over delta X, and the Taylor expansion is going to look something like, you know, f of X plus a gradient, right? So like a G transpose delta X, and then a Hessian term. So like 1/2 delta X transpose H delta X. And then the constraints, we're going to end up with C of X plus, we'll call the Jacobian of that guy, big C times delta X equals 0. And then the inequalities, same kind of thing, D of X plus Jacobian big D times delta X less than or equal to 0. And now this is a QP in delta X, right? I should be clear here. So where H is going to be D squared L dx squared. So that's Hessian of the Lagrangian, where if I just take the Hessian of the objective, this would be a Gauss-Newton. If I take the full Hessian, including the Hessian of the constraints with the lambda in there, then it's full Newton. So either way. And then the gradient, right? Gradient of Lagrangian. Big C is dc dx. Big D is big little d dx. Lagrangian is sort of x lambda mu. We've got multipliers for both the equalities and the inequalities. So that's the objective. Then we got a Lagrange multiplier on the equalities. So we'll use lambda for that one. And then a Lagrange multiplier mu on the inequalities. Cool. So we set this all up and we solve a QP over the deltas there. And that's going to give us what we call a primal dual search direction. So it's going to give us basically a Newton step, and then we can do line searchy stuff, whatever on that. So this is going to look like, so I'll do like solve the QP. That's going to give me, for example, like this delta Z thing where it's going to have a delta X, a delta lambda, and a delta mu. So it's also going to give us deltas on the multipliers, right? And then standard stuff that we've already talked about. So you can do a line search on this guy with a merit function. So we already know about merit functions, right? All the usual stuff. An alternative that you can do is a trust region, which corresponds to, rather than doing a backtracking line search, you put an explicit constraint on the norm of delta X in the QP. So that's basically, and that norm constraint is called the trust region. That's the other idea that you can do. And there's trade-offs between those two things, and it sort of depends on the problem, et cetera, et cetera. So if you only have equalities, not inequalities, this is exactly Newton's method that we did at the beginning. So you only think about it as like Newton's method, with inequalities. So if we only have equalities, equality constraints, this sort of reduces to a Newton step, Newton's method on the KKT conditions. Which we've already seen like the second week of class, right? So it's this kind of deal, right? H, C transpose, C 0, and then like a delta X, delta lambda. And then over here, you'd have minus G, like the gradient of the Lagrangian, and then minus C, the this kind of thing. And this we already know is know and love as this is called a KKT system. They show up all the time. Okay, so yeah, as I've been saying out loud, you want to think about this really as just like a generalization of Newton's method to handle inequality constraints. Cool. And in principle, you could just go code this up right now using the QP solver that you have to get the search direction, and then like Armijo line search with the merit function of your choice. So we've already kind of talked about that stuff. Super straightforward. Like you could plug and chug and do this right now. You kind of have all the building blocks. There's not really any mysteries in there. In principle, you can use any QP solver for the subproblems. But good implementations, so like SNOPT, right? Like industrial quality sort of implementations play lots of tricks. So they, in general, the move here is to try to like recycle as much as possible from the last solve inside the QP solver. So like it tends to not be a super generic QP solver. It tends to be sort of the QP solver is tightly integrated with the SQP algorithm in such a way that you can do a lot of warm starting tricks and play a lot of games to get more speed out of it, more efficiency. So that, but sort of good implementations. Will warm start using the previous QP iteration. So that's sort of, there's lots of games to play there. We can do lots of worm starting tricks from the last QP solve. In particular, like a very sort of common move is to use like active set QP methods where you kind of assume that the active and inactive inequality constraints are not changing much between iterations. That's one trick. And then the other thing, if you're doing trad problems, which we are, these problems have a ton of structure. They have a bunch of temporal structure. So remember when we saw the QP corresponding to the LQR problem and how it had all that block structure and was super sparse, and we used that block structure to derive Riccati by doing like back substitution. So that's all there. So these problems are super sparse. They have a lot of band structure. And in order to make a direct method, a SQP method like this, not suck, you have to be somewhat clever about using the sparsity structure. And most of these solvers are. Like most of these are using sophisticated sparse linear algebra, sparse linear system solvers that can take advantage of at least some of that sparsity. But all the speed wins are basically from being clever about the sparsity. So that's something to think about. And actually, you can try this out on the homework. We're asking you to do this. And we actually give you like some nice wrapper code for calling IPopt, and you can choose to call the sparse version or the dense version. And you'll find after you get to a certain size problem, like the dense version basically becomes unusable and like totally intractable. So okay, so that, and then yeah, the other sort of quick note on this is if the inequality constraints happen to be convex, i.e. like cones, you can actually include them. You don't have to linearize them in that case, and you can actually include them directly in the subproblems. And that sort of generalization of SQP is called sequential convex programming, or SCP. And this is actually super popular, like last 10 years or so. Been a lot of work on this, particularly by a guy named Betchit Achikmashe at University of Washington, who did the rocket soft landing stuff. His lab has done a bunch of SCP stuff where they essentially bake the conic constraints directly into the subproblems instead of linearizing them. So you can do that. Basically, all you really care about is the subproblems are convex and you can actually solve them. So you don't have to think about linearizing as much as convexifying. If you can like, if the stuff's convex already, just throw it in there. That. Sequential convex programming. So to be clear, SQP is a special case of SCP. And you just put those inequalities directly into subproblems. And yeah, that's super hot. There's actually, it's a good review paper in IEEE Control Systems magazine like last year with like a survey of this stuff. This has been hot for like 10 years or so. Okay, I think that's it for the solver stuff, what SQP is, how to actually solve these things. Any questions about any of this stuff? Yeah.
So before we start, you mean we start the next iteration where the previous iteration, like we initialize, like linearize on the same point.
You're going to relinearize about the new point, but often you can play games where you're like exploiting some information. You're assuming that the new QP is somehow close or related to the previous one. And so you're going to use some of that information to like try to warm start the next QP, you know, by borrowing some of the last solves information. So in particular, where this shows up a lot, which I kind of mentioned, is in active set methods. So you're assuming that the active constraints haven't switched in a lot of cases, and that can make a big difference. That's a common strategy. So SNOP does stuff like that.
Since we started with utilizing both sort of linear expansions of constraints and the objective, does the utilization step not think of the point member?
A lot. Yeah. It's just like Newton's method. Like the initial, it's non-convex problem. You need a good initial guess in general, right? And it's all local, so you're going to end up sort of in the basin of attraction, where you started, kind of thing. So that's all kind of, caveat everywhere. Okay, cool. So now we're going to talk about direct collocation, which is kind of the sort of the gold standard direct method, sort of like how DDP is kind of the gold standard indirect method. This is kind of the gold standard direct method. And there's some cool tricks in here that are worth knowing about, basically. So what you would do normally, like what we've already kind of talked a lot about and advocated, is if I give you a continuous time dynamics, throw it at RK4, right? That's kind of what we've been saying. And that's what we used in DDP and LQR stuff. And that's also what we've been doing for simulating. And that's all good. And that's, to be clear, right? We talked a little bit about at the beginning of the class. There are explicit Runge-Kutta methods and there are implicit Runge-Kutta methods. And we showed the example way back first week, right? Explicit Euler versus implicit Euler, where implicit Euler kind of had the opposite energy behavior. But the big thing there was computational, where explicit Euler, you plug in the state and it's a closed form and you got the next state. Implicit Euler, you're evaluating the dynamics at the future time step. So you end up having to set it up as a root finding problem and use Newton's method or something like that to get the next state. So computationally, a lot more expensive in general to do an implicit Runge-Kutta method. So that was the story so far about this. So just as a reminder, we've used explicit Runge-Kutta methods like RK4, where you end up with like x dot equals f of xu turning into xk plus 1 equals f of xk uk. So we just plug in chug, right? So this makes a lot of sense for those computational reasons. This is the move if you can do it for like doing a rollout. So in DDP, you're doing a forward rollout. This makes tons of sense. This is cheap to evaluate, etc. And that's kind of what we've been doing so far. But the big message here is when we do a direct method, we're not doing rollouts anywhere. Instead, what we're doing is discretizing those dynamics constraints and stacking them up as a whole bunch of equality constraints in this nonlinear program, right? They're in that C of x equals 0. They're just stacked up at all those time steps. So we're not doing rollouts anymore. And as a result, like this explicit Runge-Kutta thing doesn't matter anymore. Like explicit versus implicit, it's no extra work to use an implicit method here because I just throw it in there as an equality constraint and throw it in the solver. So this big sort of large scale nonlinear programming solver has to do the same amount of work either way. So I put another way, right? I no longer have to do that root finding problem myself. The NLP solver is solving a giant root finding problem already. So I might as well, kind of use an implicit method and maybe that has some advantage. And it does have an advantage, which is obviously why we're talking about it. So in the direct method, we're just enforcing dynamics. As equality constraints. Between knot points. So if I think about that C of x equals 0 constraint for a particular sort of pair of knot points or pair of time steps, it's going to look like, say, C sub k. It's going to depend on xk, uk, xk plus 1, and uk plus 1. In general, maybe not uk plus 1. Either way, you can do different things. So this is C of x equals 0, right? And whether that's explicit, where I sort of take the thing up here, xk plus 1 equals f of xu, and I just subtract the xk plus 1 off the other side and set it equal to 0, I could do that. That's totally valid. But I could also just throw an implicit integrator in there where the xk plus 1 is implicitly buried inside the f in a nonlinear way. It makes zero difference to the NLP solver because I just need it to look like that, right? So said another way, Whereas in a rollout, implicit integration incurs a lot of extra work and extra computational cost. It's basically free in a collocation method. And so if that's the case, maybe you want to think about this a little bit more. Okay, so digging in a little bit, a collocation method, the gist is it's going to represent trajectories as polynomial splines. So we're going to, which is kind of already happening in Runge-Kutta methods, as we've talked about. It's going to be a little more explicit here. So we're going to take the control trajectory, the state trajectory, all the trajectories, and we're going to make them splines. And for now, we're going to do the most classic version of this, which uses cubic splines, everyone's favorite spline. And basically what you do is you plug the spline in, and then you enforce the dynamics as constraints on the spline derivatives. And since they're polynomials, I can diff them in closed form. And in fact, no matter what sort of method I use to parameterize my splines, taking the derivative of that spline is actually a linear operation. It's a matrix multiply on whatever representation I use to sort of represent the spline. So that's kind of cool. Okay, so that's the general gist. You can use any order spline you want, in fact. So if you have a very smooth problem and you want really high accuracy, which is the case in a lot of aerospace problems, in aerospace problems, it's not uncommon to use like 8th order splines for collocation, for like spacecraft trajectories flying to Mars and stuff like that, where you want super, super high accuracy. In robotics, way less common, because I would say, number one, we don't care about the accuracy that much because our models aren't that good. And number two, we also often have a lot of non-smoothness in our problems, and going to higher order doesn't help you at all if the problem's not like C8 smooth, right? If you want to use an 8th order polynomial spline, that kind of implicitly means that the underlying trajectories need to be C8. They need to have like 8 derivatives that are continuous. Otherwise, it doesn't make sense. Okay, so what we're going to do right now is the most classic algorithm here, which is affectionately abbreviated DIRCOL for direct collocation, but this is the original classic paper from like the mid 80s. DIRCOL algorithm. This uses cubic splines for the states. And it uses first order hold or piecewise linear interpolation on the U's. Okay, so that's the gist. Here we go. So we're going to draw the kind of spline stuff. So just as like a cartoony kind of thing, let's imagine I have sort of t here, and this is x of t, and I have some continuous trajectory that maybe looks like this. And so what I'm going to have here, let's say I've got some time step. We'll draw a couple knot points. Let's say I've got this sort of thing. Let's say these are 2 time steps, and this is tk, and this is tk plus 1. These guys, the sort of states at tk and tk plus 1, these are called knot points. And it turns out in the middle here, we're gonna use the midpoint when we evaluate the dynamics. And I'm gonna draw this in red. So this is sort of like tk plus a half, if you like. Halfway between. This guy is not explicitly a decision variable. It doesn't show up in the optimization problem, but we actually compute it implicitly inside the dynamics constraints. And this thing is called the collocation point, or basically any points at which you're evaluating the dynamics in between the not points. These are called collocation points. For cubic, you only need one of them. But for higher order polynomials, you would need more of them, right? Kind of proportional to the order. So that's some lingo.
These are like the 4 points that I'll give for the evaluations.
Yeah, basically. It's a little different because this is fully implicit, but yeah, it's basically the intermediate evals in between the TKs, right? Yeah, so that's good. Yeah, that's sort of analogous. We don't use the same lingo for the explicit methods, but it's, yeah, that's the idea. And then for the U's here, we'll have T, U of T. This guy is sort of piecewise linear, right? So it's looking like this. Et cetera, et cetera. So then here we just have TKs. And then these are sort of the not points to be blue. And those are the U's that are in the problem. We're also going to compute midpoint values here via linear interpolation to use internally when we evaluate the dynamics. Okay, cool. That's that. So what I'm going to do now is we're going to write this down. We're going to write some math down and then kind of derive the constraints. And it's a little algebra. It's not too crazy. It's literally just writing down polynomials and taking some derivatives. So let's go ahead and do that. So what we'll do first is we'll write down x of t over a time step. It's explicitly a cubic polynomial. So I'm just going to write like a generic cubic. So I've got a constant term, a linear term. I'm just writing the coefficients, right? So the subscript here is the order on the coefficient. So that's x of t between tk and tk plus 1, basically. So here we're assuming that tk is 0 and tk plus 1 is 1 or whatever. We're scaling it down. And then x dot of t, if I just sort of diff this in closed form, right? I know how to diff polynomials. So this is C1 plus 2C2t plus 3C3t squared. Cool. So I've got x and x dot over my interval based on the cubic thing. One thing to note, right? So given this, I can actually take this, and what I ultimately want to do here is represent this spline using just information at the not points. So I want to write the polynomial spline. I ultimately want to interpolate this guy using x and x dot at the not points. Make sense? So what I'm going to do now is show you how to, it's literally polynomial fitting, which is a classic problem. So we're going to do fitting where I'm going to fit the coefficients, these C's, by knowing x, k, x dot k, x k plus 1, x dot k plus 1. So how you do that is you write a big matrix down. You write, I want to find xk, x dot k plus 1, x dot k, x k plus 1, x dot k plus 1. I want to sort of use that stuff to fit the polynomial. Oh, I did this backwards. Oops. This goes here. So given, yeah, I want to map the coefficients into those values, and then I want to invert this. So if I plug in, like basically t equals 0, and like evaluate the x polynomial, if t equals 0, it's just c naught. So that's super easy. So that's 1 and a bunch of zeros. So xk gives me c naught. Similarly for x dot, if I know x dot k, so that's t equals 0, I plug t equals 0 into the x dot polynomial, and that just picks off c1. So I get this. And now what I'm going to do is the k plus 1, where that's t equals h. That's my time step. So I plug h into the polynomial, and I get 1 h squared, h cubed. And then I plug h into the x dot polynomial. I get 0, 1, 2h, 3h squared. Cool. So now with this, I can plug in the not point stuff, the x's and the x dots, and I can solve for the c's. I can also write that the other way, right? By inverting this guy, no big deal. Maybe I'll do that explicitly here and just write it down for you because it's maybe useful. So if I invert this matrix, it turns out I can invert this in closed form. That stays the same. And then these time step things change a little bit. I'll just write them for you. I think these are useful for your homework. You can also do this with like Wolfram Alpha or any of those kind of things. Okay, so this guy times the not point stuff is going to give you the coefficients. And then with these things, you can now kind of do any kind of interpolation you want. So basically what this lets you do is given the x's and x dots at the not points, I can now evaluate the interpolated value of the state anywhere in the middle, assuming that, they're fit through a cubic spline. And that's what we want. So that's why we did that. Okay, cool. So that's all the stuff. If I now kind of evaluate the state, so here's the recipe is I've got x and x dot at the not points. I mean, I can enforce the dynamics there, no problem. But to sort of fully constrain this to have it make sense and like, be third order or whatever, I also want to enforce the dynamics somewhere else in there to make it sort of a well-posed thing and sort of fully determined. So randomly, arbitrarily, we're going to also enforce the dynamics at the midpoint. Seems reasonable. So what I'm going to do is I'm going to plug tk plus a half, basically h over 2, into all this stuff and get x at the midpoint and x dot at the midpoint. Then I'm going to just add a new constraint that's enforcing the dynamics at that midpoint. So that's the whole thing. So here's how we do it. Evaluate this thing at tk plus a half. So this would be like xk plus a half. Right, and this is, to be clear, the collocation point, as we've called it. So this is going to look like x tk plus h over 2, to be super clear. That's what we're doing. And if I like literally just plug this into those matrices, I get 1/2 xk plus xk plus 1. So that would be what you would get with linear interpolation, right? And then I get this extra term here, h over 8, x dot k minus x dot k plus 1. So that's what the x is. And now just from this, like literally all I do is, well, I've got those x dots there. I can plug in the continuous time dynamics for x dot. So I plug the f's in there, and now I have a dynamics constraint. So this is going to be xk plus 1 plus h over 8. And now I plug in f xk uk minus f xk plus 1 uk plus 1. And now I basically, and to be clear, right, these are the continuous time dynamics. This is basically like doing the integration for us kind of implicitly in the constraints, right? So there's no, basically this is your Runge-Kutta method, sort of implicitly in the constraints. Okay, so that's the first one. Then we're going to do this on the x dots as well. So you've got x dot k plus a half, which is x dot evaluated at tk plus h over 2. And if I just go plug this into the matrices and evaluate this thing, this interpolated value, I get the following. Minus 3 over 2h, xk minus xk plus 1, minus 1/4 x dot k plus x dot k plus 1. Same thing, we're going to plug the f's in for the x dots. Okay, so that's that. Then remember, we also have the u's, and for that, we're assuming linear interpolation. So this is uk plus a half. This is u at tk plus h over 2. This is just the average of uk and uk plus 1, because we're just linearly interpolating those guys. So that's the whole thing. That's everything we need. And now we're going to do the last step, which is enforce the dynamics constraints at that midpoint. So this would be some, c sub k, xk, uk, xk plus 1, uk plus 1. And this would end up being, so we have this one here where we have the x dot at the half point. That's also an f, right? So I plug in f for that. So I've got f at the midpoint, xk plus half, uk plus half. So those are all things I know how to evaluate up here. And then I plug in this guy, this second line that we just did. I get the following thing. Okay, so this whole thing equals 0. That's the constraint. And remember, this is the continuous time dynamics and all this stuff. Okay, that's the whole thing. That was a little messy. Hopefully that wasn't too terrible. Bunch of algebra. But basically, the overall recipe is we assume there's a spline connecting the knot points. We write the spline in terms of the values at the knot points. Then I enforce the dynamics constraints at that collocation point by interpolating the x's and u's to the middle and just enforcing, f has to equal x dot on the spline at the midpoint. So that's all this mess. It just comes down to that guy, that one equation. Make sense? So I wrote this in terms of xk plus half, uk plus half. In practice, when you implement it, the xk plus half, uk plus half collocation stuff is not a decision variable. It's calculated implicitly, like inside this constraint function from the xk's and uk's. So I can always evaluate those things. I can plug them in here, but they're not optimization variables. So that's important. Oops. So note that only the xk's and uk's are decision variables. Not the like half values. What else? Okay, so this thing we just did, this is called Hermite-Simpson integration. Has anyone heard of this before? Has anyone heard of Simpson's rule? This is like a classic thing for computing integrals, actually. So you have a random sort of nasty integral that you can't, integrate in closed form. A classic method for calculating the area under the curve, like computing the integral, is called Hermite integration, and it's this. You basically fit a cubic spline to the curve and then integrate the cubic polynomial in closed form, because we know how to integrate polynomials. So this is the dynamics, like ODE version of Hermite integration from like calculus. And it's called Hermite-Simpson. So that's cool. It turns out this is third order accurate. So sort of RK4 is fourth order accurate. This is third order accurate. And so this is really basically a third order accurate Runge-Kutta method. It's an implicit Runge-Kutta, third order Runge-Kutta, which is pretty good, right? Does anyone remember what it means to achieve third order integration accuracy? Yeah, it means if I analytically Taylor expand the trajectory x of t, the step I get for xk plus 1 from this guy matches exactly the first three terms in a Taylor series for x of t. Okay, and then the real kind of nugget here, which this is kind of a mess, and this is not obvious yet, is that this thing requires fewer dynamics calls than if we had done explicit Runge-Kutta. So I'm going to show you that now, which is kind of cool. So this is actually more efficient, which is kind of the whole point. So let's write that down and I'll show you. This requires fewer dynamics calls than an explicit RK3 would. Okay, so that's maybe not obvious. What it comes down to is basically the implicit version. You're recycling the endpoints sort of across time. So let's write that down to make that clear. So here's explicit RK3, very similar to RK4, just one less stage. So I'll write it down. Then so we're gonna have 3 F calls in here. And this will be, zeroed or whole or whatever. It doesn't matter, turns out in this case. The important thing is kind of how these are getting evaluated. So this looks very, very similar to RK4. I'm just writing it down for us to take a look at. So, okay, this is an RK3 step, very similar to RK4. It needs 3 dynamics evaluations per time step, which all makes sense. Like, that's all obvious. So let's look at the Hermite-Simpson thing now. And think for a sec about what it looks like. So this thing, we have a constraint that looks like this. We have f of xk plus a half, uk plus a half. So that's a dynamics call at the midpoint. And then this thing, I'm just writing the constraint function. And then this is just the constraint from before rewritten. Okay. Okay, so if I look at this and I think about this constraint like ck, so like this constraint at time k, and then this constraint at time k plus 1. The f of xk plus 1, uk plus 1 between those overlap. So one of those calls is the same. So like if I do this at 2 not point, like 2 time steps, I've got not point, f at this not point, f at this not point, f in the middle. The next time step, I've got the same, the first f call from the next one is the same as the last f call from the one before it. So those are the same f call, and I can reuse that call. So that means basically asymptotically over long trajectory, this requires only 2 f calls per time step. So it's like a third fewer function calls. And so it's actually like kind of like 30% more efficient, which is kind of a fun nugget. These get reused. So sort of, this is only really 2 dynamics calls. So yeah, and then the overall message, right, is that like most of the time in these methods, the dynamics calls and the dynamics Jacobian evaluations are one of the most expensive pieces of the whole thing. So this can be like sort of 30 to 50% savings in compute, which is kind of a big deal. Also, from our earlier discussions, implicit Runge-Kutta methods are usually better than explicit ones anyway. They usually have better like energy conservation properties and stability properties than explicit methods. So there's basically win-win. Like it's better because implicit integrators tend to be better for like physics reasons, and it's cheaper. So there's like zero reason not to do this. So basically, you should not use RK4 if you're doing direct method. Like if you're doing collocation, you should use this because it's cheaper and better, which is a rare thing. Okay, cool. So now we're going to do it. So here's some code. Apologies in advance. There's like a lot of gross looking boilerplate. Uh, so, I'll talk through it a little bit, but there's a ton of boilerplate in here. What we've done on your homework is Kevin, last year's lead TA, very nicely wrote like a really pretty one-liner that took care of all the boilerplate for you. That's mimicking the MATLAB API for this called fmincon. So the homework has this nice fmincon function. This has all the boilerplate in it, which is under the hood inside that fmincon function for you guys. So you don't have to worry about all the gross stuff. Okay, so we're using a bunch of stuff that we've used before, the robot dynamics stuff. We're using IPOpt as our solver. And then this thing, MathOpt interface, this is the Julia kind of API for doing nonlinear optimization. It's an API that can call a bunch of different solvers. So that's what we're going to use to write the problem down, and then we're going to call IPOpt. That's what that is. We're going to do an acrobot. So this is the double pendulum that we saw last time. We're going to do this at 10 hertz. It turns out you can take really pretty big time steps with collocation, much bigger than you can with DDP, because we're getting more accuracy out of the higher order interpolation. Boilerplate stuff, 5 seconds, usual kind of stuff. And then here's that constraint. So in particular, right, here's my dynamics calls. These are like those midpoint interpolated values. Note, I'm computing them from the not point values inside the function. They're not like decision variables, right? And then that's exactly what we just derived. And I plug that into the continuous dynamics. All good. Cost function, we're going to use like a very vanilla quadratic cost that's trying to get us to the goal, the upright goal, kind of exactly the same stuff we did last time. So that's the cost function. This is basically enumerating all those dynamics constraints between all the not point pairs. So it's that one dynamics constraint. I'm just instantiating it for all the time steps. So this is, on the whole trajectory, just in a big for loop. Cool. And then this is, so I've got the dynamics constraints, and then I'm also enforcing some other constraints. So one of the cool things about collocation, as we kind of hinted at, it's really good at handling arbitrary constraints. I don't have any issues with just plugging in any constraints I want, any generic inequality or equality constraint. So here I'm going to enforce a goal constraint. So the last time step, it has to be at the goal. That's what this thing says. And the first time step, I'm actually enforcing it explicitly to be at X naught. There's not really any notion that there's no rollout anymore, right? So there's nothing, the initial conditions actually have to be specified as a constraint, right? Same with the final conditions. It's all kind of the same. This is just a ton of boilerplate for interfacing with the solver. This is that MathOpt interface stuff. Don't worry about this too much, frankly. It's just Julia stuff. Yeah, I don't know. Lots of garbage. Don't worry about it. But yeah, stuff you can see in here. So you can put bounds on the variables, right? These are IPOpt actually special cases, straight up bound constraints on the X's and U's. Because if you special case those, you can be a little bit faster on them and stuff. So it's special cases bound constraints from like generic nonlinear constraints. So that's what that's about. And then the rest of this is all kind of, not interesting. It asks, so if you care, it's trying to take advantage of sparsity, but it's dumb. So you have to explicitly tell it the sparsity pattern. That's what this is. And I didn't do that, so it's going to be slow. And then, yeah, the rest of this is just giving it the cost functions. We're using forward diff to get all the Jacobians because I'm lazy. What else? Anything else? Yeah, I think that's kind of it. And then this is just calling the solver. So again, a lot of like setup boilerplate code. It's a little gross, but we've nicely wrapped it for you for your homework, so you don't have to worry about it. Initial and goal states, just like before, start down here, end up here. And then we're going to give this a very dumb guess. We're going to leave it at X naught for all the time steps. we're not going to give it any real guess. And U's are all zero. So it's just sitting here with nothing. That's the initial guess. We're going to now call the solver. I was lazy and didn't give this sparsity information. So it's actually treating this as one big dense problem. So it's really slow. It takes about 10 or 12 seconds the last few times I ran it. There you go. So here you go. This is with verbosity turned on. So it's giving us all the like diagnostic information. But the punchline is, you know, optimal solution found. Cool. Took like 10 seconds or so, 800 iterations, whatever. It gives you a bunch of like, yeah, 11 and a half seconds. Cool. So let's take a look. So this is just pulling out all the X's and U's from that stacked up. Again, I just stacked up that Z has, you know, XU, XU, blah, blah, blah. So this is the X1, X2, the joint angles. So start hanging down, end up top. Cool. Those are the velocities. So it starts at 0, ends at 0. These are the controls, sort of weird looking. Let's take a look at the animation. It's doing what you want. Okay, so now here I want to show you right before we leave one cool thing. So the big advantage of collocation methods over indirect shooting type methods is the states and controls, there's no distinction. They're all just decision variables. And in particular, I can make a guess that is not dynamically feasible. So in DDP, I have to do a rollout. So I can't guess the controls and the states independently. I have to guess controls and then roll it out. Here, there's no rollout, and I can guess anything I want for both. So a cool thing about that is, let's say you have some intuition for the problem, or you have some sample-based planner that can give you a guess solution on something. Like anything you know, you can put in here for a guess. It doesn't have to obey physics. So I'm going to do that right now. I'm going to take the solution we just got. I'm going to put just theta 1, just one of the angles in there with noise on it, nothing else. So it doesn't obey physics. It's not the whole solution. It's only one of the 4 states. But now if I go resolve this, it solved almost instantly, right? Like took 25 iterations, took like less than a second, and it got me the answer. So like to be super clear about it, right? Like here's the guess solution that I gave it. You can see like how garbage it is. I gave it this squiggly line and like zeros for everything else. And just giving it this squiggly line for one of the states was huge time savings, right? So this is kind of like a huge deal. Collocation gives you a ton of flexibility for providing these initial guesses from other places. Like anything else you can get, you can give it something that does only part of the state, kind of wrong, doesn't obey physics. That can help it get in the basin of attraction and converge really fast. So that's like another big advantage. With that, we're done. Have a good break. See you guys in another week.